Here to set up a mass spectrometer that will separate strontium ions of mass 1.45 times 10 to the negative 25 kilograms with a net charge of plus 2e from a beam of mixed ions. So the charges go through a potential difference of E, after which the beam enters a region containing a uniform magnetic field of magnitude 0.09 Tesla and perpendicular to the path of the ions. And they leave the ions at a distance x that is 1.75 meters from the entrance after going through this semicircular loop. And you can manually change the voltage, the electromotive force, the E. So in part A, in which direction must be the magnetic field point to produce the trajectory of the ions shown? So you use the second right-hand rule, and you have to put your fingers in the direction of the velocity, which is toward the top of the page, and curl them in such a way that your thumb will point toward the left, which is directed into the page. For part B, the ions travel at a constant speed around the semicircular path. Explain why the speed remains constant. We know the magnetic force, the F, acts perpendicular to the velocity. So that means because it's acting perpendicular, the force does not accelerate the ions in the direction of motion. What it does instead is it acts as a centripetal force to change their direction. Because remember how acceleration is defined as a change in velocity over time, and you can change velocity not only by speeding up or slowing down, but also by changing the direction, which is what's happening in this case. For part C, calculate the speed of the ions with a charge of positive 2e that exit at the distance x. So using the equation, r is equal to mv over qb, and rearranging it for v, that is qbr over m, the charge is 2e, which is 2, times 1.6 times 10 to the negative 19. The magnetic field is 0.09, and the radius is half of the total distance x, so 1.75 divided by 2, and then all of that is divided by the mass of the strontium ions, which were given in the problem as 1.45 times 10 to the negative 25. And when you plug all that in for the speed, you get approximately 1.74 times 10 to the 5th meters per second. Part D. Calculate the accelerating voltage, the EMF, needed for the ions with charge 2e to attain that speed you just calculated. So you're doing a conservation of energy, turning the potential energy from the charge accelerating through a potential difference. So you're turning potential energy into kinetic energy. So U initial is equal to K final. And in this case, the potential energy is Q times the voltage difference, and that's equal to 1/2 m V final squared. Notice that one of these V's, the first one, is a capital V for the potential, and the other one, the VF, is a lowercase v for the velocity. So you want to solve this for the V, which is the same thing as the EMF, that E symbol. So V is equal to 1/2 m V final squared over Q. So you're just going to plug in 1/2 times the mass of the strontium ions, 1.45, times 10 to the negative 25th, times the velocity that you just got, 1.74, times 10 to the 5th, and that is going to be squared, divided by Q, which is the 2, times 1.6 times 10 to the negative 19. And you get a voltage of 6,860 volts. And for part E, for strontium ion of the same mass but a charge of plus 3e enter the magnetic field at the same speed, would the distance x be greater than, less than, or the same as the distance for the plus 2e ions? So using the equation, R equals mv over qb, if the mass doesn't change and the velocity doesn't change, and they're in the same magnetic field, if only the q is changing and it's increasing as q goes up, that means the r, the radius of the path, will go down since they're inversely proportional to each other, which means that the x, which is the exit distance, will also go down. So the answer to check is that it is going to be less than.